Look at the primes. 3, 5, 7, 11, 13. 3 and 5 differ by 2. 5 and 7 differ by 2. 11 and 13 differ by 2. Pairs of primes separated by exactly 2 are called twin primes. 2 is the smallest possible spacing for two odd primes. The list of known twin pairs goes on. 17 and 19, 29 and 31, 41 and 43, 59 and 61, 71 and 73. Computers have found over a quadrillion of them. The twin prime conjecture says there are infinitely many. We don't know. The conjecture has been open for over a century. But there is a different question, easier to state. What if we don't try to count them? What if we just add up their reciprocals? For every twin pair p and p plus 2, take 1 over p plus 1 over p plus 2. Sum these over all known twin pairs. As you go further out, primes get sparser, so each term gets smaller. The question is whether the running total grows without bound or settles down to a finite value. There is no obvious reason this should converge. There are still infinitely many things to add if the twin prime conjecture is true. The reciprocals shrink, but they shrink slowly. In 1919, a Norwegian mathematician named Viggo Brun proved that the sum does in fact converge to a finite number. This was a shock. The reason it is shocking is because of what the corresponding question looks like for ordinary primes. To see why Brun's result is surprising, compare it to ordinary primes. Euler proved in 1737 that the sum of 1 over p, taken over all primes p, diverges. It grows without bound. The growth is slow. It grows like log of n, but it never stops. The result is profound. It implies primes are infinite in number, which Euclid had already proved. But it implies more. It says primes are not too sparse. They are dense enough that the harmonic-style sum still diverges. If primes were as rare as squares, the sum would converge. The sum of 1 over n squared is famous. It equals pi squared over 6. Bounded. Finite. Primes are denser than squares. The sum of their reciprocals diverges. So when Brun asked the same question for twin primes, the natural guess was, this also diverges. After all, conjecturally, twin primes are infinite in number. Their density follows a predictable rule. Hardy and Littlewood, in 1923, conjectured that the count of twin primes up to n grows like 2c2 times n over log squared n. If you plug this density into a reciprocal sum, you get something growing like log n divided by log n. That converges. So heuristically, the sum should be finite. But heuristics aren't proof. Brun needed to show convergence using only what was known. He couldn't assume Hardy-Littlewood. He couldn't even assume there are infinitely many twin primes. So he proved it from scratch. Here is what Brun proved in 1919. The sum over all twin prime pairs of 1 over p plus 1 over p plus 2 converges to a finite number. That number is called Brun's constant. Brun himself never computed it. He just proved it was finite. His method was new. He invented a sieve technique that combined the ancient sieve of Eratosthenes with combinatorial bounds. The key step: he proved that the count of twin prime pairs up to n is bounded above by a constant times n over log squared n. That is the same rate that Hardy and Littlewood would later conjecture as the exact asymptotic count. Brun's bound was an upper bound, not the precise count, but it was the right order of magnitude. From this upper bound, Brun deduced that the sum over twin primes of their reciprocals converges. The deduction is short. Pair the terms by size. The contribution of all twin pairs in the range from 2 to the n through 2 to the n plus 1 is bounded above by the number of pairs in that range, which is at most c times 2 to the n divided by n squared, times the largest reciprocal in the range, which is at most 1 divided by 2 to the n. Multiplying these and summing over n gives a series that obviously converges. Done. The technique Brun invented is now called Brun's sieve. It is one of the most important tools in analytic number theory. Without it, we would not have most of the results about prime gaps from the last century. the Zhang theorem on bounded gaps, the Maynard sieve. All trace back ultimately to Brun. Brun proved convergence, but didn't compute the value. 40 years went by before anyone tried seriously. The first numerical estimates were rough. Estimates in the 1960s and 70s put Brun's constant somewhere around 1.90. Tighter estimates required computing the partial sum out to enormous n beyond what early computers could handle. The structure of the computation is brutal. You enumerate all twin prime pairs up to n. You add their reciprocals. You get a partial sum. The partial sum approaches b from below, extremely slowly. The tail of the series, from n to infinity, contributes a value you can only bound, not compute exactly. So your final answer is the partial sum plus an estimated tail correction. In 1994, Richard Crandall and others pushed the computation to n equals 10 to the 14. They estimated b as approximately 1.902161. In 2010, Thomas Neasley and Dominic Clive pushed it to n equals 2 times 10 to the 16. Their estimate, with rigorous error bounds, gave b equal to 1.9021605832. That's the current best value. We know it to 10 significant figures. We do not have a closed form expression. We do not have a proof that it is irrational. We do not have a proof that it is transcendental. We know its decimal expansion to high precision, and we know almost nothing else about it. It is a number that exists because primes behave a certain way. We can compute it. We cannot describe it in closed form. The sieve technique Brun invented is worth seeing in outline. The sieve of Eratosthenes works by inclusion-exclusion. To count primes up to n, you start with all integers up to n, then subtract multiples of 2, multiples of 3, multiples of 5. You add back multiples of 2 times 3, 2 times 5, 3 times 5. You alternate signs. This is exact, but for large n it requires summing over too many small primes. The error term is too big to be useful. Brun's insight was to truncate the inclusion-exclusion early. Instead of going all the way down to alternating signs over every prime up to root n, he stopped after a small number of levels. The truncated sum still gives a valid upper or lower bound on the count, even though it is no longer exact. By choosing how deep to truncate, Brun could trade between the accuracy of the bound and the cost of computing it. For twin primes, he picked a truncation level that gave a usable upper bound of order n divided by log squared n. The trick works for any sieve problem, counting integers with some property defined by divisibility. Twin primes are integers n such that both n and n plus 2 avoid divisibility by all primes up to root n. Apply the sieve to this two-condition set and you get an upper bound. Brun's sieve was generalized by Selberg in the 1940s, by Friedlander and Iwaniec in the 1990s, and by Goldston, Pintz and Yildirim in 2005, leading to Zhang's proof of bounded gaps in 2013. The whole tower of modern prime gap theory rests on Brun's truncation idea. Brun's theorem is precise. It is also limited. It tells you the sum of reciprocals of twin primes converges to a finite number. It does not tell you whether there are infinitely many twin primes. This is important. The sum could converge if there are only finitely many twin pairs. It could also converge if there are infinitely many, as long as their reciprocals shrink fast enough. The convergence is compatible with both. So Brun's theorem doesn't settle the twin prime conjecture. It restricts how dense twin primes can be, but it doesn't say whether they go on forever. The same situation appears elsewhere in number theory. Mersenne primes are primes of the form 2 to the p-1. We know 52 of them. Their reciprocals sum to about 0.51. The sum looks finite, but we don't know if there are infinitely many Mersenne primes. We have no theoretical control. The contrast with ordinary primes is sharp. For ordinary primes, the sum of reciprocals diverges. That fact proves they are infinite. Convergence of a reciprocal sum gives no such guarantee. In short, Brun's bound is on density, not on count. Densities can be zero in the limit, while counts are still infinite. The twin prime conjecture remains officially unresolved. Brun's bound gives us a ceiling. Twin pairs can't be too dense, but no flaw. In 1994, a mathematics professor at Lynchburg College named Thomas Nicely was computing Brun's constant. He was using a small cluster of personal computers, including a brand new Pentium. His program computed twin primes up to 10 to the 14 and summed their reciprocals. He ran cross-checks, compute the same partial sum on different machines and compare. The Pentium gave answers that differed from the rest in the 11th decimal place. He emailed Intel. Intel's first response was politely dismissive. Probably a software issue, please check your code. Nicely checked his code. The bug was not in his code. The bug was in the Pentium itself. The Pentium FPU used a lookup table for division. The table had 5 entries that were not properly populated. They were zeros instead of the correct values. For specific divisor patterns, the Pentium would return slightly wrong quotients. The error was on the order of 1 part in 10 to the 11th, which is enough to corrupt high-precision arithmetic. Once Nicely went public, the news exploded. Intel initially offered replacement chips only to users who could demonstrate the bug mattered for their workflow. The PR backlash was severe. Intel relented within a month and offered free replacement to anyone who asked. The total charge to Intel was $475 million. A bug that affected one division in 9 billion was found by someone summing twin primes for fun. This is a recurring pattern in mathematics. A problem that looks pure, adding numbers nobody cares about, turns out to be the most sensitive test of computational arithmetic ever performed. Brun's constant is a number that came out of a question about prime distribution, but it sits at the intersection of several deeper structures. It is bounded above by the value Hardy and Littlewood conjectured in 1923. They wrote down a heuristic for the count of twin primes up to n, in terms of a constant C2 equal to about 0.660161. From C2, you can predict B with high precision under the twin prime conjecture, and the prediction matches the computed value of B to within numerical error. This is suggestive. The Hardy-Littlewood conjecture is unproven. If it were proven, we would have a closed-form expression for B in terms of C2 and standard constants. We do not have this expression as a theorem, but the numerical agreement is so strong that almost no one doubts the conjecture is correct. Brun's sieve technique, the actual tool he invented, has been the foundation of nearly every breakthrough in analytic number theory since. Selberg's sieve, the combinatorial sieve, the polynomial sieve, the truncated chain sieve, all trace back to Brun's idea: truncate inclusion-exclusion to trade exactness for usability. When Zhang proved bounded gaps in 2013, he used the GPY sieve. The GPY sieve used Selberg's sieve. Selberg's sieve used Brun's. When Maynard simplified Zhang's proof in November of that year, he used a multi-dimensional version of the same idea. A Norwegian mathematician asked, in 1919, whether the reciprocals of twin primes could be summed. The proof he needed forced him to invent the most important tool of 20th century prime number theory. The constant is 1.902160. We know 10 more digits. We do not know if it is irrational, but we know exactly how to use the technique that proved it exists.